All right. I think we can get started. Hello, everyone. Welcome to our AI Rounds. AI Rounds is a special seminar series that is dedicated to the topic of AI for healthcare. And this is a monthly event. And today we are very fortunate to have Mamdani to join us to give this talk. And it's really my honor to introduce Mohammed. So Mohammed is Vice President of Data Science and Advanced Analytics at the Unity Health Toronto. He's also the Director of University of Toronto Trinity Faculty of Medicine Center for AI Research and Education in Medicine, or TCARM for short. Mohammed's team focus on bridging advanced analytics, including machine learning with clinical and management decision-making to improve patient outcomes and hospital efficiency. Mohammed is also professor in Department of Medicine of the Trinity Faculty of Medicine, the Leslie Dan Faculty of Pharmacy, and the Institute of Healthy Policy Management and Evaluation of the Dalla Lana School of Public Health. He also is affiliated at the ICS, also Vector Institute. And in 2010, Mohammed was named among Canada's top 40 under 40. He has published over 500 peer-reviewed publications, and he's been really the kind of global leader in pushing AI for healthcare, particularly focusing on the implementations, which I think is extremely important, because we see lots of research papers published, but the adoptions of AI in healthcare still remain very rare in real clinic. And Mohammed is really kind of the leader in this aspect. All right, with that, Mohammed, all over to you.
Thank you so much, Bo, and thank you for the very kind introduction. I'm going to share some slides. I think everyone can see them. Yeah? Very good. Yeah, if you can't see them, let me know. So I have a few objectives. Yeah, fantastic. Thanks. I just have a few objectives for today's talk. First is to understand the emerging applications of AI in healthcare. Second is to review basic challenges to applying AI in healthcare. And third is to review emerging networks in AI in medicine. I'm going to go through just some kind of headlines that people are probably seen this to death already. We speak so much in the media about how our healthcare system just isn't working, how we have wait times for medical procedures that are at a 20-year high in Canada. It's nearly 75% of Ontario doctors experienced burnout during the pandemic. 90% of nurses considering leaving the profession in the next year. Of course, some of these are very exaggerated statistics, but they do kind of center around this theme of our healthcare system needs help. And I think anyone who works in healthcare would very much agree that our healthcare system does really need some help. Now, with all these doom and gloom stories, every now and then you'll see an article like this, how AI is helping shorten patient wait times. So there's this kind of glimmer of hope, and people get excited about, well, what is this AI thing? Now, I'm not going to go into any of the details around generative AI and ChatGPT and all the press that's getting. I think it is going to be fairly fundamental, but ChatGPT has certainly increased the visibility of AI, I guess you could say. I don't think I need to say any of this to this crowd, but just in case to baseline, what is AI? AI, according to this definition from Coursera, uses computer science and data to enable problem solving in machines. My own personal definition of AI, it's basically a discipline that is focused on understanding complex relationships in data. That's really, from my perspective, what AI is about. Machine learning is a subset of AI. And I know for some of the old schoolers and some people are more traditionally trained in statistics and epidemiology, many are used to actually having a lot of control and visibility over how they construct their models. You can define weights and parameters and all that sort of good stuff. Machine learning tends to actually learn on its own, as the name would imply, that the computer systems actually learn and adapt automatically from the data they're given. So what is deep learning? In my humble opinion, deep learning is more complexity, more data. Typically, it's a subset of machine learning. And again, I'm not going to go into any detail around these things because I think this crowd is pretty well educated on what AI is and the facets of machine learning and deep learning. I am going to talk a little bit about how AI has been receiving so much attention lately, maybe a bit too much to some extent. It's viewed as a revolutionary technology. And Bill Gates writes a blog, and in one of his blogs, he had written, "In my lifetime, I've seen 2 demonstrations of technology that struck me as revolutionary." Of course, the first one is his own, the graphical user interface for computing, and the second one, of course, is artificial intelligence. So again, some people would view Bill Gates as a bit of a skeptic, but I think a lot of people are fueling AI as a major technology that we all should be paying attention to. Of course, there's other people who say, well, some people can get rich studying AI. Me, I make money studying natural stupidity. There's intentions in that as well, and that works for others. I want to step back though when we talk about healthcare and medical care, about the basic functions that clinicians do. So as clinicians, what do? We make a diagnosis. We then have a strategy, treatment, or management plan based on the prognosis of the patient. And that's kind of how we do things. And one would argue, then we communicate. This whole act of diagnosing, prognosing, and treatment decision-making is often based on a cognitive process, right? So in some cases, the diagnosis is very simple. For example, you have a blood test for a certain bacteria, you suspect an infection, you put in a culture, the bacteria comes up as a certain type, you have an antibiotic that'll kill that bug, and you're done. But in other cases, it's a bit more complicated. So for example, when we look at mental health, we get the diagnoses quite wrong often. Even something as common as asthma is an example that I often use, where there are studies now from, I believe the US, I thought there was one from UK, certainly one in Ottawa. The one in Ottawa brought in over 600 patients that were diagnosed with asthma, and over 80% of them, I believe, were being treated for asthma. And the researchers stepped back and said, well, let's actually do the proper test, because you may not have had all the data to make your decision around this diagnosis. Let's do a proper spirometry, lung function test. Let's do some proper assessments and see if you actually have asthma. About a third of patients did not have asthma, right? So again, we struggle a bit sometimes at making the diagnosis. Then, of course, there's treatment. How do we actually decide? Well, I'm going to be very aggressive if I know this patient is not going to do well. If they're not going to do well, I am going to be picking therapies where I know they have high effectiveness. Maybe they have some high side effects as well, but I know it'll be beneficial for the patient because the effectiveness is so high. In other cases where the prognosis may not be as severe, you may be a little bit more gentle, pick treatments that may not be as effective, but also have fewer side effects. The problem is you're deciding on the treatment based on what you think what will happen to the patient, or prognosis. And study after study after study has shown how poor we are as clinicians at prognosis. So then, of course, we get to treatment. How do you decide on what treatment? In many cases, you have a lot of options. I'm going to pick the example of depression. There's examples of multiple sclerosis, all sorts of conditions. In depression, how do we decide? We have options from serotonin-specific reuptake inhibitors, SNRIs, we have Mayo inhibitors, TCAs, we have a whole bunch of options to choose from. Let's say I've got 15 to 20 different drugs I can choose from to manage this patient's depression. How do I pick? A lot of clinicians, what they'll do is they'll step back and they'll say, I'm kind of experienced with this one drug that seems to work kind of well in some patients, maybe another drug that works well in other patients. I don't really know, but the drug rep came in about 4 months ago and told me about this new medication, so I'm going to try it. That's kind of how we make a decision, right? And then we get the patient back in the office 2 to 4 weeks later. We assess to see if it's made a difference. If it hasn't, we try something else. So there has to be a better way to do this. And a lot of these decisions are based on what we process in our heads. Because when we're looking at diagnosis, prognosis, and treatment, we're often thinking about things like social history, family history, lab values. We're looking at medical imaging results. We're looking at vital signs, symptoms. All that sort of stuff gets processed in our heads when we're actually making these decisions. And this is where I think AI can come in where we have issues around cognitive load. Why is cognitive load important? Well, they say the modern complex medical decision involves considering hundreds of parameters. And yet, Miller from the 1950s, who's a famous psychologist, was able to show that the average human can process 7 plus or minus 2 things at the same time, right? But cognitive load doesn't seem to be as much of an issue for machines. And that's where one area where I think they can really help is to ease that cognitive load. There's a lot of, and there's other areas where I think AI would be beneficial, including taking away so many administrative and burdensome tasks so that clinicians have more time to spend with patients and actually provide more human care. But how do we get from all this research that we're seeing these days to actual practice? If you look at the literature, there's a ton of activity, right? If we look at 2005, 2006, there were a couple hundred papers published each year on machine learning. Fast forward to 2019, not even 15 years later, over 12,000 publications, and it continues to increase. And I think we'll continue to see more and more activity. Where does it hit in medicine? Practically every discipline, right? From oncology to surgery to pathology to ophthalmology. Practically every area of medicine has had some sort of study involving machine learning. If we look at how people are trying to turn these research findings into actual products or translate them into practice, we actually have more and more machine learning enabled devices that have been FDA approved. So if we look literally just maybe 10, 15 years ago, there were maybe a handful in the FDA. Now there's hundreds that are available that are FDA approved. So the growth in trying to adopt these technologies or have them approved from the market has been growing considerably as well, exponentially. And that's also driven the market size that investors and finance people like to see. Estimated market size of around 11 billion or so in 2021, expected to rise to almost 200 billion in 2030. What about AI in Toronto? We're really, really fortunate to be able to live in this incredible ecosystem of AI because we do a lot of research, right? We do a lot of research. And why is that? Well, we're very well positioned to do research in this area. We have the University of Toronto, who has world-leading departments in statistics, computer science, engineering, education, medicine. World-leading, right? I think we have one of the top 5 medical schools in the world here. Our stats program is fantastic. Engineering is exceptional. Computer science is exceptional. Education is exceptional. We also have really, really good institutes like the Vector Institute who focus on artificial intelligence. And we have this really fantastic ecosystem of the Toronto Academic Health Science Network that encompasses numerous hospitals across the greater Toronto area, which is really, it provides a really rich clinical environment for AI. There's lots of examples of work that people do. So Sick Kids, for example, has an algorithm that will detect up to 70% of heart attacks in kids. And I think it's about 20 minutes advanced or something, which is wonderful. If we look at Princess Margaret Hospital, they've developed a prostate cancer algorithm that develops radiation treatment plans that typically take hours, if not days, for a team to develop because they have to be so specific around how much radiation, where to give, for how long. And it takes a lot of resource and time. And this algorithm that they've developed can do it within minutes with an 88% success rate. This is UHN. I believe they've actually deployed this one, which is really, really exciting. Then, of course, we have breast cancer around Sunnybrook, which an algorithm that predicts response to chemotherapy, first line chemotherapy with 96% accuracy, which again is really exciting because oftentimes, you treat a patient and they don't do well first line, then you got to go to second line. How can we improve that? Well, there may be a way to do this with AI. And of course, at Toronto General, you have, sorry, I'm not sure if I was supposed to name the person, but Dr. Mamdani, who's doing some incredible work where he's actually using AI to guide surgery. So if you look at to see how this works, this is laparoscopic cholecystectomy. Basically, what he's doing is he's using this device to say, hey, if this is green, I can cut. If it's red, I shouldn't cut because there's a higher chance of causing major bile duct injury. And it actually guides the surgical procedure in real time, which is super exciting. Now, one of the things I struggle with is, why are these things not in clinical practice right now? Of course, I know there's a lot of testing that needs to be done and all that sort of stuff, but I would love to see more and more of this incredible research activity going into practice. But as we all know, it's hard. While we see glamorous claims in the media, in the literature about how AI could transform healthcare, when we actually try and deploy these things, it is not so pretty. There's lots of failures that we can learn from, right? In 2016, Microsoft released a chatbot called Tay. Many of you have probably heard of Tay, but the thought was actually pretty interesting, right? We have a chatbot. We will create one that is so good, it'll pass the Turing test, that people will not know that it's a chatbot. They'll think they're talking to a human. Well, how are they going to think they're talking to a human? Well, we'll train it so it actually does talk to humans. And we'll ingest data from humans to actually make it more human-like. How do we do that? Let's put it on Twitter. So somebody came up with a brilliant idea of, let's throw it to Twitter and it will converse with humans and it'll learn all sorts of slang and concepts and such. It'll be wonderful. So they put it out into the Twitter universe. Within 24 hours, they had to pull Tay out because the Twitter trolls jumped on Tay and taught it to be extremely racist and misogynistic. Of course, some people had fun with it, but the point here was that it will learn what you give it. And if you give it garbage or biased or racist or misogynistic data, it will learn to be biased, racist, misogynistic. It learns from what you give it. And that's a huge learning for people. Then there's the example of Google in the early days when they had this incredible algorithm that detects diabetic retinopathy. So among patients who have diabetes, they can detect they often develop eye disease. How do you screen for it? Well, you can actually do an eye scan and see if they actually have eye disease. Now, you need experts to actually review these scans. And that takes a lot of time, energy, and resource, a human resource that a lot of countries simply don't have. So Google developed this algorithm, detects diabetic retinopathy just as well, if not better, than the world-leading clinicians. Wonderful, right? Government in Thailand says, hey, can you help me here? Because I want to do a national screening campaign for diabetic retinopathy. I would love to use your algorithm. Google says, of course you can use it. They deploy it in several clinics. They quickly realize, I trained this algorithm on really good, clean research data. Well, here's the problem. Over 20% of images in the real world are under poor lighting conditions. So the algorithm didn't work. It got confused because it wasn't trained on that data, which reflects the real world. And so it started failing and patients had to be rescheduled and everything was a mess. So they actually pulled it out. So on one hand, you can give it really dirty data and it'll learn very dirty things. On the other hand, you can give it really clean data, it'll learn really clean things, but it won't reflect reality. So getting that right is pretty important. And then, of course, there's systematic reviews like this. This is just one of them, where they actually have reviewed what's out there in the literature. In this case, it was specific to AI tools that were developed to help the COVID problem. And what they found was, after reviewing about 400 studies that were published, the lens they took was, how many of these can actually be deployed into clinical practice? And the answer, unfortunately, was not very many. In fact, this article will tell you it's 0. So why? Because the research was brilliant. Why can't you just deploy it? There's a lot more to it than that. So I'm going to go through a case example. This is just our experience at Unity Health in terms of our AI program. And we're very, very focused on deployment and how we've tried to tackle this with a lot of learnings, successes, but also some failures as well, where hopefully we can actually share this with other organizations that are trying to do something similar. Very briefly, what is Unity Health? Unity Health is a composition of St. Michael's Hospital, St. Joseph's Health Center, and Providence Healthcare. We have over 11,000 staff, over 5,000 medical trainees and health professional leaders, over 1,500 physicians, about almost 1,200 researchers and scientists and such. Our volumes, we see over 1.5 million, or we have over 1.5 million ambulatory visits every year, over 170,000 emergency department visits, over 350,000 inpatient visits. Why am I saying all this? Well, if you multiply that by 15 years of historical data, that is a lot of data to play with. So we actually have quite a bit to work with. The other thing that's really important about Unity Health, though, is that Unity Health has declared AI as a strategic pillar. We have 8 strategic pillars. In fact, we've declared AI as a core strategic pillar. What that means is we give it a lot of priority. We have 3 core strategic pillars. AI is one of them. So that means from top down, it is a priority at our institution because we see the value of it. What that means is that we have a dedicated data science team. So I have a team of about 30 data scientists, and we have developed and deployed over 50 AI solutions into clinical practice. So a lot of experience, some failures, some wins, and a lot of learnings. So how did we structure our program? The structure is actually fairly simple, very common sense type stuff. First of all, you can't do AI without data. So you have to have a team focused on the data. This is our data integration and governance team. Basically, this is a team of data engineers, ETL developers, data modelers, architects. Their whole job is, we're not on a modern EPR yet. We're going to Epic soon. I understand UHN is on Epic. So we have over 50 different source systems that don't talk to each other. So how do you get data pinging production servers too in real time? How do you get data in real time from the different systems, bring it in, do real-time cleanup, feed it into a machine learning algorithm in real time, spit out the results, feed it back to the clinicians in an understandable manner, all in real time? That's what this group does. So data wrangling, data cleaning, feeding into algorithms and such. The second group then actually develops the algorithms. So this is the advanced analytics team, and it's composed of computer scientists, statisticians, engineers, where they will actually say, all right, this is a problem that looks like it needs an XG boost. That's what we'll develop. Or this is an optimization problem, and we'll develop a sophisticated optimization algorithm. So depending on the nature of the problem, they'll get data from the data integration and governance team, and they'll build the models. Of course, a model is wonderful, but the vast majority of clinicians, I would argue, would have no idea how to interpret raw output from a machine learning model. And they shouldn't. That's not their job. They're not trained to do it. So we have a product development team. Now, this product development team is headed up by an incredibly talented individual who actually has more of an arts background. But he went and did a Master of Science in Applied Computing. And his passion, while he can develop algorithms himself, is not so much on the development side, it's more on the product side. How do humans interact with AI? So he has a team of software developers, human factors, and design experts, where they're really meticulous about, tell me about your workflow, tell me how this fits in, tell me what this looks like, what it feels like, how would you interact with it? That's really what they focus on. And of course, once you have a product, how do you deploy it? So we have a product management and deployment team, where their job is, first of all, to manage us internally and get all the right people together, but also liaise with the clinical teams. Also to be on the floors and go through education programs and go through deployment, actual hands-on deployment work right in the midst of clinical activity. So they're focused on that side of the house. How does a model work? Well, these 4 teams work together with our clinicians because we're not a research shop. We don't let research drive our work. We let the problems or the end users drive our work. It's a fundamentally different model. So again, researchers don't get to define our problems. Our data science team doesn't get to define our problems. It's the frontline staff, the ones who are working day to day and understand the issues, they get to define our problems. So anyone in our organization can pitch an idea. And when you pitch an idea, there is an intake process that we have. So the process is actually fairly simple. There's a form that needs to be filled out. Now, we fill it out with you, so you don't have to take the form. And there's a lot of rough one. So with the intake process, there's a few sections in the form. The first is, tell me about the problem. Like, what are you trying to tackle? But also, I want you to quantify the magnitude of the issue. How bad are you at it right now? And if you don't have the numbers, let's try and help you get the numbers. We want to know that it's a big problem that you're trying to tackle. The second part is, okay, now that we understand the problem, tell me how you think AI would help. You may not know a lot about AI, but tell me what you think it can do for you. The third part of the intake process is the outcomes box. And this one is incredibly important. It basically says, what outcomes are you going to impact if we actually build a solution for you? Because you should tell us what you're going to do with the data, with the model, but what your interventions are to actually change things. So your outcomes box is fairly simple. It's not a free text box. You have options. Your options are limited to death, readmission, length of stay, human effort, cost, and other. And if you click other, and that's the only box you click, typically we deprioritize you. So we're very focused on the types of things that we want to accomplish. And of course, once you actually tell us what outcome you want to impact, we ask you by how much. So if you clicked mortality or death, tell us how much are you going to drop it by? Oh, 10%. Great. Because when we co-develop the solution with you and we deploy it, we're going to evaluate it. And if we don't meet that 10% reduction benchmark, then we either sunset the project or we have a conversation of why we're not hitting our targets. So we do have this very deep process around solutioning, where if you propose the idea and you're really passionate about it, you have to agree to sit in meetings with us. And our meetings are every 2 weeks. And there's a lot of work in between meetings as well. But every 2 weeks we're meeting, and you're going to meet with the data science team, with our clinical folks, with other folks that are involved. It's very multidisciplinary, and we're going to co-create the solution together. And in fact, many of these meetings will expect you to lead because you're the subject matter expert. And then, of course, once we've actually developed the solution, we deploy it, and then we actually look at outcomes to see if we're meeting the targets that we had said we would meet. This is just a snapshot of the different types of solutions that we have. I don't expect you to read in detail. The point of this slide, though, is that you may notice that we have solutions that are all over the map. So we don't take an oriented approach or a targeted approach where we say, we're only going to tackle cardiology, or we're only going to tackle the emergency department. What we do is have a focus on, we're only going to tackle things that clinicians are passionate about, and they could be from anywhere. But if you're really, really passionate about it, those are the projects that we want, because that means you're driven and that you've bought in and you're motivated. The other thing you have to motivate is your colleagues. So we're also cognizant that we also need 3 signatures on the intake form: your medical director, your program director, and your division department head. They have to sign off as well, because everyone has to agree this is a big problem and you've got a community tackling this rather than a single individual trying to drive things. So what are the sorts of solutions that we've developed and deployed? I'm going to highlight 3. I should probably update this slide because I seem to use the same examples. We've got over 50 of these things, but I'm going to highlight 3 of them. On the more kind of operations end, our nurses came to us very early on, and they had said, here's a problem that we struggle with: assigning nurses to the zones in the emergency department. And our data science team initially said, are you kidding me? That doesn't sound like a great use of our time. And they said, no, my gosh, are you kidding me? It's one of our top 3 stressors. And we said, could you please explain to us why this is such a big deal? And they said, you guys are so naive. Here's the issue. We have a lot of rules that we have to adhere to. So when we assign nurses to the different zones in the emergency department, we have to adhere to rules like a junior nurse has to be with the senior nurse, has to be with the team lead. You can't have the same nurse working in the same zone with the same person in the past 48 hours. There's all sorts of these rules that we struggle with. And it makes it complex for us. And then people are not happy if we have violations of these rules, and we get that all the time. And if somebody calls in sick, we got to do the whole thing all over again, which happens all the time. So we asked, what's the magnitude of the problem? And they said the magnitude of the problem is, number 1, we spend 2 to 4 hours every day on this task with our team. 2 to 4 hours. The stress levels I can't quantify for you, but they're pretty high because of all the anxiety we have to deal with people and us. But 2 to 4 hours every day. Our repeat rate, or the times that we get it wrong, is over 20%. And we said, okay, good. 2 to 4 hours is a lot of time. 20% plus error rate is pretty high. So we developed an optimization algorithm with a software solution. And what it does is it basically actually kind of watches or keeps track of all the nurses, of where they worked, when, with whom. And it actually then optimizes the allocation. So you can click a button and it'll actually do your assignments for the next 4 days. If something changes, somebody complains or somebody's sick, you putting up their name, say sick, it redoes all the assignments. So it's been running for actually almost 5 years now, I think, and actually 4 years, about 4 years. And the time spent has went from 2 to 4 hours every day to under 15 minutes. And the repeat or error rate has went from 21% to under 5%. So they're seeing actually considerable impact on human effort, which is exactly the type of thing we want to see. In our multiple sclerosis clinic, the more senior neurologists, not so much, but the junior neurologists, the residents, the fellows, and the newer neurologists, often they struggle with, how do I get all the information I need when I need it? And it may be a lot better at UHN and other groups that have modern EPRs. You may be a lot better at it than we are, but it is a slog to get the information that you need. Especially if a new clinician is there and saying, all right, I've got 10 minutes in between patients. I just finished seeing a patient at 3 p.m. My next patient is at 3:10 p.m. Oh my gosh, they have multiple sclerosis and they have 7 years of history. How am I going to review 7 years of history in 10 minutes? So working with those clinicians, they told us, here are the things that I would like to see. And luckily, we were able to get at all the things that were important to them. So things like, when do they have a relapse? What sort of meds are they using? What were the medical imaging results on their MRIs? Things like that were really important to them. So we have something called Muskrat, or the Multiple Sclerosis Reporting and Analytics Tool. Basically, what it does is it actually creates a timeline visual of the patient's events. So it's able to tell you over a timeline, the patient had a relapse here and here and here. Look, they had one 6 months ago. You tried these medications 3 years ago, you switched them to this, and now they're on these meds. They had new lesions on their MRI in their brain 2 years ago. They had another one 6 months ago. And if you're interested and you say, I wonder what happened here, you can click on it and it'll actually bring up the entire medical imaging report for you. It also tells you about disability scores and progression. And so you know that if the patient's on a pretty bad trajectory, you need to be more aggressive in your management. 7 years of history, it summarizes all of that in about 2 seconds. So the physician history has a pretty good synopsis, so they can actually go in and have a more informed discussion with their patient. That's not perfect, so sometimes I've got a few things wrong, but the accuracy is generally pretty good. Then, of course, the last one is clinical prediction that I'll mention. It's an early warning system, and there's a lot of early warning systems out there, but to my knowledge, none of them really work well. So there's one in Epic, for example, that has received a lot of criticism, and it may work well for some hospitals, but I know in our organization, it probably wouldn't, because we have an understanding of how the high false alarm rate, and there's all sorts of other issues. So we've created one that works for us. The way it works, we call it ChartWatch. It's designed by clinicians for clinicians, so they had a huge say in terms of the model thresholds and parameters and such, in terms of how often they want to be alerted, the accuracy levels, all that sort of stuff. So what ChartWatch does is it monitors all of our general internal medicine patients. So at St. Mike's, if you come and you're internal medicine, you will be monitored by this algorithm. We've deployed it in another surgical unit. We're deploying it in other units as well St. Joseph's Hospital in the new year. So we're expanding the deployment. But what it does is it runs every hour on the hour, and it's been trained on over 20,000 patients worth of data. So every hour it's running and it's grabbing all sorts of data, and it's predicting if this individual patient is going to die or go to the ICU in the next 48 hours. And it categorizes patients as low, medium, and high risk. As soon as it reaches a high risk threshold, it pages the medical team. It's all automated, so nobody has to do anything. It pages the medical team. In our protocols, the medical team has to come and see the patient within 2 hours of being paged. And then there's all sorts of care pathways, increased monitoring to Q4, look for signs of sepsis, initiate antibiotics. We've deployed it in October of 2020, so we have about 3 years of experience, and we're just about to submit a paper on this now. Our best guess is well, not best guess, but the results of the study are showing well over 20% reduction in mortality. So it's heartening to see that these things can actually help save lives, which is wonderful. I'm going to go through some considerations. The implementation. People will talk about bias assessment, and I think it's incredibly important. I'm going to say something that may be controversial and may not sit well with a lot of people. I think we need to be practical about bias assessment. So what do I mean by that? Well, I'm going to use ChartWatch as an example. Again, we've seen over a 20% reduction in mortality. Did we test it among young versus old? Yes, we did. Among males versus female? Yes, we did. Among sick versus not so sick? Yes, we did. What about race? No, we didn't. Why? Because we don't have race data. What about gender as opposed to sex? We don't have gender data. What about socioeconomic status? We didn't, because we don't have socioeconomic status data. So we had to make a decision. At what point are you satisfied with bias assessment? And I don't think there's a lot of good guidelines around exactly what constitutes a fulsome bias assessment, or at least a general agreement around them. Because from my perspective, practically, I can look at 40 different parameters around bias. And I'm almost certain that if I go to a conference and present, somebody will raise their hand and they'll say, well, you didn't do 41, 42, and 43. When does it stop? And when do you make a judgment that it's good enough? And the other ethical consideration is, well, we could actually pause the algorithm that's reducing mortality by over 20% until we get race data, for example. Is that okay? Luckily, we live in a very multicultural city where we have good representation of a lot of races, a lot of genders, a lot of different types of people, where I'm a little bit more comfortable. But is the bias assessment thorough? Maybe, maybe not. But certainly the impacts are there. Then, of course, there's ethics assessment. There are some algorithms that are very sensitive. That we have one, for example, that identifies patients that may not want to be identified. But these are patients that need care and need help. And if we don't identify them, how can we provide them the care and the expert consultations we need to provide them? So is it more of a, yeah, we have to respect the patient? Absolutely, we do. But at the same time, our medical team is saying, I need to help these patients, but I don't know who they are. So we get stuck sometimes around, do we deploy them or not? We actually have one stuck for over a year now, just going through ethics discussions and acceptability discussions. Communication and clinical validation. Clinical validation is absolutely key. And communicating around what this algorithm can do and, more importantly, cannot do. What do I mean by clinical validation? I'm just going to touch on that. A lot of times we go into an algorithm and we say, this is great performance, when actually it's not, right? I'm going to use a very simple metric of accuracy. Somebody can come up to me and say, my algorithm is 96% accurate. And I can legitimately look at them and say, that is not very good, because our clinicians have 98% accuracy. Another person can come up to me and say, my algorithm has 76% accuracy. And I can say, that is fantastic, because our clinicians have 52% accuracy. But accuracy of what? And oftentimes we don't do the due diligence and the homework to around what our quote unquote standard of care is. And in many cases, our standard of care is physician opinion. So what ChartWatch, what we did is we went up to the floors and we asked our doctors, nurses, and our residents, do you think this patient's going to die or go to the ICU? Because that's how you make decisions. It's based on your opinion. And we were able to show, we have over 3,000 clinician predictions. We were able to show that the algorithm performs considerably better when it's paired with clinician judgment compared to clinician judgment alone. We needed to show that for there to be buy-in. In fact, one of the metrics is that when we ask clinicians and they say this patient's going to die in the next 48 hours, they're right less than a third of the time, right? Again, we struggle with prognosis. External validation and explainability. I'm going to just touch on that. Lots to talk about external validation. Very important, not for us. Reason why is because we're only worried about our hospital. Do we need it to be externally validated? Absolutely not. We need it to be validated internally because that's all we care about. Now, if we wanted to send it to other hospitals, absolutely external validation becomes very important. But it's only relevant for the purpose that you drive it towards. Explainability is another issue. Some will argue, and I think explainability is absolutely necessary, so I'm not knocking explainability. I'm just thinking, have a practical approach towards explainability. Because sometimes we want to know, why does the algorithm predict what it does? And we have to remember, people can provide Shapley values and reduce it to very singular linear types of features and such. But oftentimes when it does that, it's telling us stuff we already know, right? And we tried that with ChartWatch initially. Actually, we said, here's the Shapley values, here's what's driving things. And the response we would get is, this is dumb, I already know that. Well, of course you already know that, because it's linear, it's simple. The complexity is around all the interactions of these subtle things that you may not have thought of that are so hard to explain that the machine is picking up. How do we explain that in an understandable way? That is hard. The other thing that we do that I kind of cringe a little bit about is we hold things to a much higher standard, as we should to a certain extent. But sometimes it's unreasonable. And what I mean by that is there's a great example that Leo Celli from MIT uses quite often. He'll ask people, do you use acetaminophen? And of course, most clinicians will raise their hand and they'll say, of course I use acetaminophen. But can you tell me the mechanism of action? Because nobody in the world knows how it works. But you use it, right? Of course. Why do you use it? Because it works. Well, if an algorithm is actually reliably, reproducibly putting out good results, why are we so fussed? So I think we need to really rethink about how we're actually thinking about explainability. Certainly there is value because we want to know, well, are there things that are wrong with the algorithm or things that, for example, bias issues we need to understand through explainability. But I think practically when you deploy, I think there is some context that's needed here around explainability. We do soft launch, so we do a lot of silent testing. And silent testing typically is highly variable depending on the nature of the project, how many outcomes are planned. So for example, if we have an algorithm that has very rare or a condition that is fairly rare in terms of outcomes, we'll need a longer silent testing period. Whereas if outcomes are more common, you need a shorter silent testing period. But we do silent test quite a bit. And then of course, evaluation. Implementation and post-implementation is very key in terms of communication. When you're communicating during the development, it's a very different ballgame than when you're communicating after you deploy. You just have to keep reminding people it's real now. And actually, these are the limitations. You remember, right? It's magical how they forget when they're so excited. And then when it comes real time to actually deploy, you got to remind them. And of course, monitoring, evaluation, and maintenance. Maintenance is absolutely key. What about data shifts, data drifts? What about model degradation over time? Who's watching? Because if a model performs now, well now, does it perform well 6 months from now, 8 months from now? What happens if you change the reagent of a lab test? Does that screw up model results? It absolutely can, and that's been our experience. But who's watching? Our data scientists take call. So there's always somebody on call 24/7 in case there's substantial degradation or there's data shifts that we didn't expect. And that's happened a couple of times. Or there's data pipeline failures. That's happened fairly often, actually, in some cases, especially when in the early phases. So who's watching and who's maintaining? The resources that have to be put into that as well. There's lots of guidelines out there in terms of how you actually develop these things. So the US, the Health Canada, and the UK have got together and put out good machine learning practices for medical device development. And they provide some really useful thoughts. We've written a paper actually reviewing this and applying it to a real world example of our early warning system, ChartWatch, and going through the GMLP saying it's a great start, but I think we need more. We need to up our standards because these things are used quite religiously by many people and can have profound implications in how it actually shapes medical decision making. So in summary, our approach is one, the AI lab. So this is what a lot of hospitals do. They have a really nice research environment. I'm not knocking it at all. It's a good compute environment. You cut some data and you play. Researchers drive this process and they publish papers. That's what we've done, but that's not where we stopped because that's not really the game that we had in mind. If you want deployment, you have to go to, at least I'm convinced, a living lab environment. And that's a very different model because now it's no longer the researchers driving things. It's the clinicians and the end users who are often not researchers, who are often not data scientists. They get to drive the questions. It's not the researchers anymore. You also have a machine learning operations environment, which is very different from a research compute environment. Machine learning operations environment is nimble. It actually really focuses on real-time data that's changing, that's dynamic, that cleans things in real time. Very different setup. And then, of course, there's data governance. Hospitals have a huge propensity to say no to everything that's innovative because we are conservative, people's lives are at stake. I get it. But how do you actually create a progressive governance framework that allows or enables AI for the right people to be able to access the right data at the right time? That was really critical for us. And so at our hospital, we are one of two groups that gets access to a lot of data, let's say, a lot of sensitive data. Because our argument when we were creating the program was, if it's Mr. Jones who's going to die in the next 48 hours, we need to know it's Mr. Jones. Like we can't just say this is the de-identified key number that you have to unscramble, clinician, that takes out another, you can't even do it. We have to be practical about it, right? So we have, I would argue, the most progressive data governance framework in the country. And then, of course, how do you deploy to other hospitals? This is something that we failed miserably at. We're just not very good at it. And the reason why is because we're not positioned to do it. What do I mean by that? We're going to use a case example of an emergency department volume forecasting algorithm. So we have an algorithm that runs regularly. What it does is it predicts how many patients are going to come to our emergency department over the next 7 days. So the immediate prediction is for 3 days, and then there's an extended prediction for 7 days. The way it works is it grabs 4 years of historical data. We have it scraping the web for weather data. Is there a snowstorm happening tomorrow night? We have it scraping the web for city planning data, long weekends and such. All that information goes in the algorithm, and it's able to tell you today is, for example, Wednesday. We can tell you Friday from noon to 6, there'll be 82 patients waiting in the emerge. 10 of them will have mental health issues. 12 of them will be hard to treat. The rest will be easier. Our accuracy is between 94 to 96% typically. It just helps with planning and staffing. Present this at a conference. There's a dozen hospitals that say, oh, we want this. We said, great, you should have it. You should be using it for planning purposes. But a half a dozen of them come up and say, hey, can we actually have it? Like, really, we're serious? We said, yeah, sure, of course. So we actually sent them code. And of course, the response we get back is, we don't understand Python and R. So could you help us? Why don't we send you data? They actually sent us timestamp data. So it's not PHI, it was actually fairly safe. Put in the algorithm. We actually gave them results daily. And the response was, we don't understand machine learning output. Can you develop the dashboard for us? So we did. And we just didn't want to be in a position where we're now the IT help desk and support and ongoing maintenance and monitoring for hospitals that are outside of our venue. And we're not even funded to do it. There's no liability, there's liability issues. There's all sorts of issues there where we got really nervous. We were convinced that we just can't do it ourselves. So we actually were fortunate enough to work with an incredible business entrepreneur type. He used to be the chief AI officer for TD Bank, Tomi Putinen, who said, I'd love to be able to get into the healthcare space. And we said, terrific, could you? So we asked him and he said, yes. So Signal One was launched in April of 2022, just last year. And so they take a much more responsible approach and a dedicated approach to say, how do we get some of these things into other hospitals? I'm just going to touch on AI medicine networks. I want to talk a little bit about how people can learn more about AI, whether it's very simple concepts or more advanced concepts, and how we actually come together as a community. We have lots of hospitals in our TASM network. We have hospitals around the country. We have clinics around the company, but a lot of us don't talk to each other, right? How do we break down the silos? We had this really nice donation from the Temerty family to the University of Toronto, where we created the Temerty Center for Artificial Intelligence Research and Education in Medicine, or TCARM, at the University of Toronto. The goal really here is to advance AI medicine through a multidisciplinary collaboration between relevant stakeholders, including healthcare providers, statisticians, computer scientists, engineers, and industry. We launched in October of 2020, very much as a team sport center. The types of things that we do, we have a community of over 1,000 members now with 24 universities across the country and over 90 organizations. We have international partnerships with India and Israel, Technion in Israel and IIT in India. From a research perspective, we typically give out a little over $700,000 a year in grant funding. In education, we have monthly speaker series that are fairly well attended. We have trainee rounds. 80 to 100 trainees typically attend from all sorts of disciplines like computer science, engineering, statistics, medicine, all learning from each other. We have a data environment up on Google Cloud called the Health Data Nexus, where we have publicly available data sets so you can actually do analytical work. We have about a half a dozen data sets now, and we're hoping to grow it to quite a few more, where the access by researchers and students has been made so much easier because you need data to do AI. We also belong to a global community of AI medicine called ACAM, or excuse me, the Alliance of Centers of Artificial Intelligence in Medicine. There's over 50 of these centers that meet regularly, monthly, and we're one of them. Last year, we were named Institution of the Year because of the work that we're doing at TCARM. And so this is where I think people who want to learn, be part of a community, it's been well funded by the Temerty family. There's no cost to people who want to join. I would say anyone who wants to learn and be part of a national and now global network, join TCARM at the University of Toronto. We'd love to have you. And this is how I think we're all going to come together, learn from each other, because certainly we've had successes, but we've also had failures. We'd love to learn from others as well. And this is how I think we're going to be able to develop solutions, deploy them, and provide better care for all of us. And I will end here.
Thank you so much, Mohammed. Fantastic talk. Lots of food for thought. So please, for audience, please input your questions in chat or simply just raise hands. Kelly and I can coordinate the question QAs. Yeah, Sarah.
Yeah, hi. Thank you so much for.
You're muted.
Sorry, I know, but you click the button twice. What happens? But it's great to have this presentation. Bo, I'm delighted to have heard it. And Mohammed, I would like to spread the message. I'm very interested about this transition to Epic. As you know, it's going to be, I can't.
Me too.
Well, maybe you know what my question is then. How do you work with what you've got and then migrate to a new system with new data parameters and so on? And maybe just a little insight on that would be very helpful for me. But just thank you again. It's a great presentation. And I think the way you've operationalized is a real learning for all of us.
Oh, thank you, Sarah. I think from my perspective, we're going to know a lot more in the next, I would say, 6 months or so. What we're bracing ourselves for is a period where we go dark a little bit and transition as much as we can to the Epic environment. We're fully cognizant that some of it will be fairly easy to translate into, others will not. And they'll have to stay a standalone and feed into Epic somehow. So our data engineering team is learning a lot from Epic in terms of what can and can't be done. So I imagine it will be messy for the first little while, and then we'll just we'll adapt. As much we can shift over to Epic, we would like to. But we're also cognizant that, number one, not everything will shift over. Number two, their compute environment, we won't be using that. We've already made a decision on that we're going to keep what we have. We have a Linux-based compute environment that we're actually pretty happy with. And what they have wouldn't meet our needs. I hope that helps.
I'm still muted. The other question would then be, is there anything, Bo, that we could do in our pre-production environment that might help Unity test things? And I don't know. I'm just trying to think about some things that might actually help facilitate success for you. And given that we already have an existing environment, I'm just trying to think a little bit outside of the box.
Fantastic. Yeah, it'd be great to chat if there is area for collaboration. It'd be wonderful to explore it, because we would love to learn, and we have things that we could share as well.
Yeah, likewise. I think also Angela have a similar question. Do you have concerns on how AI will be deployed after Epic implementation? I think you have briefly touched upon that. Yeah,
I wish I had more information on it. We just don't know enough yet about how painful it's going to be. We know enough to say that it will be painful, and not everything will be able to be transferred.
Yeah. And also, I particularly like your kind of very fresh point that, everyone talking about explainability, everyone talking about bias, but also you provide a very fresh perspective from how being practical, right? Do we wait to have a very thorough, to go through all the list to 100 items, or do we start implementation right now after certain amount of validations? That's a very perspective to me. All right, I think.
Yeah, go ahead.
Sorry. Yeah, go ahead. We have another hand, Patrick.
Thank you very much. My name is Patrick Rogala, radiologist at JDMI. Brief question. I was very intrigued by what you said about the nursing and the plan, etc. But how much of this work is actually only data access and data processing without actually a prediction model, which then comes at the end? Is that the major part of it, or can you quantify this for me?
Yeah, it's a great question. I would say I think we probably spend more time on data acquisition and processing than the actual algorithms itself. If I had to I know the rules that people put out there is 80% of your time will be on data wrangling and processing, and the rest will be on actual machine learning algorithms. If I had to guess, it's not too far off. We spend a lot of time on data acquisition and prep. And I don't know the Epic environment. I'm not sure if it's going to get much better through Epic. I'm hoping it gets better, but I'm imagine it would go down from 80% to 50% maybe.
Yeah. Thank you very much.
Oh, my pleasure. Yeah, our data engineering team has grown considerably because of exactly this. We're finding we spend much more time on it.
Does your data engineering team actually work in that clinic setting?
No, so the data engineers typically, well, actually, I shouldn't say that. The way our meetings are scheduled is that we have not constant, but very regular engagement with the clinicians. So every 2 weeks, we have exposure to the clinical team. We do site visits. So all of our teams, so in each of the 4 different groups, all of them actually go on the floors and actually see what's happening in the environment. And sometimes we'll go in multiple times just to kind of get a sense of are we actually kind of understanding the problem right. But the one that's on the floors and doing stuff with the clinical teams the most is the product management and deployment team. Yeah.
Thank you. Yeah, maybe given the time limit, we just take the one last question from Matthew. He's saying, thank you for another great talk. I'm curious if you are doing or looking at applications of large language models.
No, you know what? We haven't. We've been playing with instances of Falcon for 8 months now, I think. So we've been playing with that for a little while. We're still worried about the whole hallucination thing because we want to use it more for clinical purposes. I think it can be used for other purposes that we just haven't deployed yet. I know UHN is a leader in this space with clinical camel. It looks very exciting. So we haven't done that sort of work. What we'd love to use it for are things like writing up our docs notes for them. But what we're finding is when we do that, the rate of hallucinations is high enough that the clinicians may say, oh, you know what, it's not acceptable. I'll give you an example. We actually had a demo from a vendor on this. And we've seen it. I think ours performs a little better, but the vendor, when they demoed it for us, it was going through an actual conversation that 2 clinicians were having with each other. One was pretending to be a patient. The other one was doing a clinical assessment. And there was a large portion on musculoskeletal conditions that the patient didn't have. It just made it up for some reason. And when we asked our physicians, does this sound okay to you? They said, nope, it would take me longer to go through and figure out what's wrong and fix it than if I just wrote it up myself. So when it gets better, I'm hoping we'll be able to go into that space a bit more aggressively.
That's interesting. Maybe we should test our clinical camel.
We would love that. That would be great. Because we're really looking for good solutions. And I know you've done a lot more work on it than many other people have.
Yeah. All right. I think we're running out of time. Thank you so much, Mohammed. This is really fantastic talk. We learned so much. And also, we're gonna for all the people, thank you for attending. And we're gonna send out. I think the light is out. We're gonna send out the survey just to collect some of the feedback, and we will have our next AI round November 1st, which we're gonna send more details later on. All right. Thank you, everyone. Have a great day.
Thank you, everyone. Bye.
Thank you. Thank you.